Imagine standing at the edge of the universe, a space traveler with a telescope that can peer into the very fabric of reality. When you scan the sky, you see many star systems, each one a unique canvas of planets, moons, and cosmic phenomena. The lens of your telescope focuses on one system that's very similar to our solar system. For a moment, you feel a familiar sensation, a cosmic déjà vu, but as you get closer, the differences become apparent. Planets are not where they should be. Moons are too many or too few. And then, as you stumble upon yet another system, you suddenly realize that what you're seeing is a cosmic anomaly in the vastness of the Milky Way. What if we told you that our solar system, the cosmic neighborhood we call home, is that very anomaly? Despite the billions of stars in our galaxy, each potentially containing its own family of planets, our solar system stands out for its uniqueness. Recent research and mathematical models have begun to peel back the layers of this cosmic mystery, revealing startling truths. This is not just a story of stars and planets. It is a story of cosmic good fortune. Let's explore why our solar system is a rarity in the universe. In the annals of human history, the stars have always been a source of wonder and curiosity. However, our understanding of our cosmic neighborhood has undergone dramatic changes over the years. In ancient times, people predominantly believed in the geocentric model, which considered the Earth to be the center of the universe. This model was widespread until the Renaissance, when it encountered its first serious problems. Nicholas Copernicus turned the geocentric model upside down by proposing a heliocentric model, placing the sun at the center. This was a radical shift that laid the foundation for modern astronomy. Fast forward to the 20th century, and we meet figures like Carl Sagan, who popularized the idea that our solar system is not unique, but rather one of countless others. Sagan's work instilled a sense of cosmic humility, emphasizing that we are but a pale blue dot in a vast cosmic ocean. For many years, the scientific community has operated under what we might call the commonality hypothesis. This was the belief that the architecture of our solar system was common to the entire galaxy, a belief supported by the lack of contrary evidence. However, the launch of the Kepler telescope marked a paradigm shift. Its discoveries challenged the commonality hypothesis, revealing many stellar systems that defied our traditional understanding. So at the crossroads of history and discovery, we cannot help but wonder, is our solar system a cosmic anomaly? The answer to this question not only changes our historical understanding, but pushes us into a new era of space exploration. And as we'll see next, this understanding is more fluid and exciting than we ever imagined. Let's start by taking a closer look at this silent guardian that has quietly revolutionized our understanding of the cosmos, the Kepler Space Telescope. Launched in 2009, this marvel of modern technology had one primary mission: to detect Earth-like planets orbiting other stars. Kepler's mission was groundbreaking. It aimed to answer the age-old question, are we alone in the universe? To do so, he focused on a specific region of our galaxy, simultaneously observing more than 150,000 stars to detect the characteristic dimming that occurs when a planet passes in front of its star. The data sent back by Kepler was genuinely revolutionary. It revealed not only individual planets, but entire planetary systems, many of which were not comparable to our preconceived notions of what the solar system should look like. Kepler's discoveries were a wake-up call. They challenge the long-standing commonality hypothesis by showing that our solar system may not be as typical as we once thought. Most of the planetary systems discovered by Kepler had nothing in common with our own. One of the most startling discoveries was the rarity of systems like ours. According to Kepler, solar system-like configurations make up a tiny percentage of the galaxy's planetary systems. Although the Kepler mission ended in 2018, its legacy lives on. It paved the way for future missions, such as TESS and the James Webb Space Telescope, which aim to delve even deeper into the mysteries of the universe. As we move forward in this narrative, keep in mind that the Kepler telescope didn't just read textbooks. Kepler's discoveries fundamentally changed our understanding of planetary systems, setting the stage for subsequent discoveries. So, what we now know. The universe is a grand canvas of diversity. Star systems, the building blocks of galaxies, have many configurations, each with its own unique set of characteristics. Let's start with the most common types: binary and triple systems. In a binary system, two stars revolve around a common center of mass. According to scientists, these systems make up a significant portion of the known stellar systems in our galaxy. Triple systems are a step higher in complexity and have 3 stars. These systems can perform complex orbital dances that are marvels of gravitational physics. However, the universe is not limited to 3. There are systems with multiple star clusters, rogue planets not orbiting any star, and even systems with stars ejected due to gravitational interaction. But what does this diversity of systems mean for our understanding of the universe? When we include our solar system in this cosmic composition, it stands out as an anomaly. Unlike the more common double and triple systems, our solar system is a single star with a diverse set of planets, satellites, and smaller bodies such as asteroids and comets. According to some reports, single-star systems like ours make up a tiny percentage of the galaxy's planetary systems. In a universe full of diversity, we occasionally stumble upon something eerily familiar. One such cosmic curiosity is the star system 55 Cancri, located about 41 light-years away in the constellation Cancer. At first glance, 55 Cancri appears to be a cosmic twin of our solar system. Its main star, a yellow dwarf, very similar to our Sun. It also boasts a family of at least 5 known planets, one of which is a super-Earth located in the star's habitable zone. The super-Earth, known as 55 Cancri E, is about 8 times heavier than Earth and orbits its star at a distance that could potentially allow for liquid water on its surface. This has led to speculation about the possibilities of life. On closer inspection, however, the differences between 55 Cancri and our solar system become quite apparent. The orbits of its planets are more eccentric, and it does not have a gas giant like Jupiter, which plays a crucial role in the stability of our system. 55 Cancri emphasizes the rarity of a system like ours. Even this seemingly similar system has key differences that set it apart, making our solar system an even more unique cosmic object. In the quest to understand the uniqueness of our solar system, mathematics offers a language that goes beyond speculation. A recent study by researcher Lokesh Mishra and colleagues present a model-independent framework for characterizing, quantifying, and classifying the architecture of planetary systems. Lokesh Mishra, an astrophysicist who has made significant contributions to the field, emphasizes the need for a standard model of planet formation. He and his colleagues have presented a new mathematical framework for quantifying the similarities between planets in a system. This framework can help uncover patterns that reveal the general rules that govern the birth and growth of planetary systems. Mishra believes that in a few years, we'll have something like a standard model of planet formation that will answer how different planetary system architectures arise. The study proposes to categorize the architecture of planetary systems into 4 classes: similar, mixed, anti-ordered, and ordered. Jan Alibert, another key figure in this study, explains that this classification is based on the mass or size of the planets and their location in the system. Alibert notes that this basis can also be applied to other dimensions, such as radius, density, or water fraction. Studies show that such architecture is the most common result of planet formation. These systems often inherit their mass architecture from the mass architecture of their core, providing a strong link between a planet's internal structure and its system architecture. Interestingly, anti-ordered systems are expected to be rich in so-called wet planets, while most observed ordered mass systems are expected to have dry planets. This discovery has implications for the search of habitable worlds. The mathematical prism through which we can view the universe not only quantifies but also categorizes the amazing variety of planetary systems. Dr. Lokesh Mishra notes that similar planetary systems are the most common and make up about 8 out of 10 planetary systems visible in the night sky. On the other hand, ordered architecture, which includes our solar system, seems to be the rarest. So where does our solar system fit into this mathematical structure? The study doesn't address this issue directly. However, it does mention that ordered architecture, the class to which our solar system belongs, is a rare result of planet formation and is found in about 1.5% of designs out of 1,000 simulations, further emphasizing its exceptional nature. But what conditions give rise to systems like ours? Every star system begins its life in a molecular cloud, a dense and cold region of space filled with gas and dust. These clouds serve as cosmic wombs where initial conditions set the stage for the formation of stars and planets. The first act of star system formation is gravitational collapse. When the elements of a molecular cloud are pulled together by gravity, they begin to stick together and form a protostar, the precursor of a star. Once the star is born, the remaining material around it begins to coalesce into planets, a process known as planetary accretion. And that's where the architecture of the stellar system begins to take shape, influenced by factors such as angular momentum and elemental composition. Given the many ways in which these initial conditions can be altered, it's not surprising that our solar system is a rare result. The specific conditions in the molecular cloud that gave rise to our system must have been exceptionally unique to result in such a rare architecture. In many ways, the formation of a star system is like a cosmic lottery, governed by both chance and the law of physics. The odds of creating a system like ours, it's astronomically low, which makes our existence all the more remarkable. The rarity of our solar system doesn't just make us unique, it also raises intriguing questions about the search for extraterrestrial life. If our type of planetary system is so rare, what does that mean for the likelihood of finding life elsewhere in the universe? One of the most pressing issues in the search for extraterrestrial life is the question of habitability. The conditions that make Earth habitable are complex and interrelated. If the architecture of our solar system is rare, then the specific conditions that led to the emergence of life on Earth also inherit that rarity. Life on Earth exists in a variety of extreme environments, from acidic lakes to the crushing depths of the ocean. Can life exist in the extreme conditions found on exoplanets of different types of planetary systems? The goal of the search for extraterrestrial intelligence, or SETI for short, is to detect signals from other civilizations. If our type of planetary system is rare, the types of planets targeted by SETI may need to be reconsidered. Could it be that we're looking in the wrong places? The Fermi paradox asks why, given the vast number of stars and planets in the universe, we have yet to find evidence of extraterrestrial life. The rarity of our solar system adds another layer to this paradox. Could it be that the conditions for intelligent life are even rarer than we thought? After studying history, delving into the mathematical intricacies, and pondering the existential questions raised by our unique place in the universe, it's time to reflect on the profound implications of the rarity of our solar system. The existence of our solar system is a delicate balance between chance and the immutable laws of physics. It's a cosmic lottery in which the odds are astronomically low, and yet here we are, pondering our own existence. Our very existence is intertwined with the cosmos. The elements that make up our bodies were forged in the heart of the stars, and the conditions that led to the emergence of life on Earth are the result of the unique architecture of our solar system. The search for life elsewhere is far from over. The rarity of our solar system complicates this quest, but it also fuels our curiosity. It compels us to look further, ask deeper questions, and explore the uncharted territories of our cosmic neighborhood. Our solar system may be a rarity in the great tapestry of the universe, but it is the starting point for countless adventures still to come. In the vast expanse of space, among the countless stars twinkling in the night sky, celestial events of unimaginable scale and power take place. Events that eclipse entire galaxies and reverberate throughout the universe. Today we will delve into one such event, the stellar cataclysm known as a supernova. From ancient civilizations that saw these events as omens to modern astronomers studying them to understand the universe, supernovae have always fascinated us. Recently, the star Betelgeuse has dimmed dramatically, leading some scientists to speculate that it may soon turn into a supernova. If it does, it would be the brightest supernova observed from Earth in more than 400 years. Today we're going on a journey to understand these stellar cataclysms and their impact on our planet and their story of our place in the cosmos. We dive into the fascinating world of supernovae. In the great theater of the cosmos, the stars are the protagonist. They are born, they live, and they die. But some stars give such a spectacular performance in their final act that it outshines entire galaxies. They are supernovae, the catastrophic death of stars. But what is a supernova? Simply put, a supernova is a powerful and bright stellar explosion. It occurs during the last stages of a star's life, when the nuclear fusion in its core can no longer support the outer layers of the star. This causes the nucleus to collapse under its own gravity, leading to a violent explosion that can briefly obscure the entire galaxy. The energy released by a supernova is so enormous, it's equivalent to the energy that our sun would radiate over its entire 10 billion year lifetime. Supernovae are not just fascinating cosmic phenomena. They play a crucial role in shaping the universe. They are responsible for the distribution of elements throughout space, elements necessary for the formation of planets and life as we know it. In fact, it's believed that most elements heavier than iron, including gold and platinum, were formed by supernova explosions. So the gold in your jewelry, the iron in your blood, the calcium in your bones, all of these were once part of a star that was cut short by a spectacular explosion. Long before telescopes, space probes, and modern astronomy, ancient civilizations were already observing the stars. They noticed patterns, mapped constellations, and recorded celestial events. Among these events were the sudden appearances of new stars, which we now know as supernovae. One of the earliest recorded observations of a supernova was made by Chinese astronomers in 185 AD. They described a guest star that appeared in the sky, was visible in daylight for several weeks, and disappeared after about 8 months. We now know it was a supernova, and its remnants, known as RCW86, have been observed with modern telescopes. Another famous historical supernova is SN 1054, Crab Nebula. discovered by Chinese and Arab astronomers in 1054. This guest star was about 4 times brighter than Venus and was visible during the day for 23 days. The remnants of this supernova are what we now call the Crab Nebula. The ancient observations of supernovae had a profound effect on the way these civilizations understood the cosmos. They challenged the idea of an unchanging universe, an idea prevalent in many cultures. They were also used for astrological predictions and were often seen as omens. Today we continue to study supernovae not as omens but as opportunity to learn more about the life cycle of stars, the creation of the elements, and the history of our universe. Although our understanding of the cosmos has grown, these stellar explosions continue to fascinate us with their power and mystery. Recently, the star Betelgeuse in the constellation Orion has attracted the attention of astronomers. Betelgeuse, a red supergiant, is nearing the end of its life, and at the end of 2019 it began to dim dramatically, leading some to speculate it may soon become a supernova. However, it has since returned to its normal brightness. The most widely accepted explanation for this event is that the star emitted a large dust cloud, which obscured some of its light and made it dimmer from our perspective on Earth. When the dust cloud dispersed, Betelgeuse's brightness returned to normal. This serves to remind us the universe is not a static place, but a place where stars are born, live, and die in spectacular ways. Every star in the night sky has a story to tell, a story that begins long before we see its light. The life cycle of a star is a journey of transformation, from a mere cloud of gas and dust to a beacon of light that can outshine a galaxy. The journey begins in nebula, a huge cloud of gas and dust. Inside these cosmic nurseries, pockets of gas and dust begin to collapse under their own gravity. When they collapse, they heat up and form a protostar. Over millions of years, the protostar continues to gather mass from the surrounding nebula. As it grows, the pressure and temperatures in its core increase. When the core temperature reaches about 27 million degrees Fahrenheit, nuclear fusion begins. The protostar is now a main sequence star, just like our Sun. A star can remain on the main sequence, burning hydrogen in its core for billions of years, but eventually the hydrogen fuel runs out. What happens next depends on the star's mass. In stars the size of our Sun, the core shrinks and heats up, causing the outer layer to expand. The star becomes a red giant. Eventually, the core collapses and the outer layers are ejected, forming a planetary nebula. This leaves a white dwarf. But as we travel through space, we find that not all stars meet their end in the same way. A star can also go supernova. Its type will largely be determined by the mass and composition of the original star, while also having its own unique characteristics. For example, spectral analysis of Type 1 supernovae lack hydrogen lines. The most famous subtype, Type Ia, occurs in a binary stellar system. A white dwarf, the dense remnant of a star similar to our Sun, sucks matter from its companion star. Once the white dwarf reaches a critical mass, it undergoes a thermonuclear explosion, resulting in a supernova. On the other hand, Type Ib and Ic supernovae are thought to result from the collapse of the cores of massive stars that have lost their outer layers of hydrogen, and for Type Ic, helium. Now, let's focus on one of the most common types of supernovae we observe, Type 2. These supernovae originate from the massive stars much larger than our own Sun. Stars with at least 8 times the mass of the Sun can undergo this dramatic transformation. Throughout their lives, these massive stars are in a constant battle between gravity pulling inward and the force of fusion pushing outward. When a star exhausts its nuclear fuel, gravity wins the battle. The core of the star collapses under its enormous gravity. This collapse of the nucleus occurs incredibly quickly, in just a fraction of a second, and leads to a powerful explosion, a supernova. the outer layers of the star explode in a spectacular spectacle, outshining the entire galaxy for a short time. What's left of the star may form a dense neutron star, or if it was massive enough, a black hole. But the legacy of the star lives on. The explosion disperses the elements formed during the life of the star into space, seeding the cosmos with building blocks for new stars, planets, and even life. When a star goes supernova, it's not just a spectacle of light. It's one of the most energetic events in the universe. The amount of energy released in a supernova explosion is so enormous, it's equivalent to the energy the sun would radiate over its entire 10 billion year lifetime. But where does all this energy go? Most of it is carried away by neutrinos. These tiny, nearly massless particles are produced in huge quantity during a supernova. They travel at nearly the speed of light, taking about 99% of the explosion's energy with them. The rest of the energy is released as light and other forms of electromagnetic radiation. This includes gamma rays, the most energetic form of light, and X-rays, which are less energetic but still much more powerful than the light we see. The visible light from a supernova is so bright that it can briefly obscure the entire galaxy. This light can be seen at great distances, making supernovae important cosmic beacons for astronomers. Although supernovae are interesting to observe, they can also pose a potential danger. The enormous energy and radiation released in a supernova explosion can have significant consequences, especially if the supernova is close enough to Earth. One of the main causes of concern is the impact on our planet's ozone layer. The ozone layer acts like the Earth's sunscreen, protecting life from the sun's harmful ultraviolet radiation. But an intense gamma-ray burst from a nearby supernova could destroy the ozone layer, increasing the amount of UV radiation that reaches the Earth's surface. This increased UV radiation can have harmful effects on the Earth's biosphere. It can lead to higher rates of skin cancer in humans and other animals, and disrupt photosynthesis in plants, potentially affecting the entire ecosystem. In addition to gamma rays, the supernova also emits a stream of high-energy cosmic rays. These particles can further damage the ozone layer as well as create streams of secondary particles in the Earth's atmosphere that would increase the radiation dose. In our study of the dangers posed by supernovae, there's another interesting aspect to consider: gravitational waves. These are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Albert Einstein predicted the existence of gravitational waves in 1916 in his general theory of relativity. Einstein's mathematics showed that the massive accelerating objects like a neutron star or a black hole orbiting each other would collapse space-time in such a way that distorted space waves would emanate from the source. And supernovae, with their incredible mass and explosive energy, are the first candidates to create such waves. When a massive star collapses and explodes, the asymmetry of the explosion can potentially create gravitational waves rippling through space. These waves will be incredibly weak by the time they reach us, and will pose no danger to Earth, but they give us a new way to study the universe. Scientists have already begun to detect these waves with incredibly sensitive instruments, ushering in a new era of gravitational wave astronomy. Fortunately, the probability of a supernova exploding close enough to affect Earth is quite small, but understanding these potential dangers is crucial. It's a reminder of our connection to the cosmos and how events occurring light years away can have consequences right here on our home planet. As we've seen, supernova explosions are powerful events that can have far-reaching consequences. But did you ever guess that supernovae may have played a role in shaping Earth's history? Scientists have found evidence of past supernovae in the form of iron-60, a radioactive isotope in ancient geological layers and cores of Antarctic ice. Iron-60 is not naturally produced on Earth, but created by supernovae. suggesting that our planet was dotted with the remnants of these stellar explosions. One notable event is the Pleistocene supernova, which erupted about 2.7 million years ago. Some scientists speculate that this supernova may have affected Earth's climate during the Ice Age, perhaps even contributing to a period of cooling. There's also a theory that supernovae may be associated with mass extinctions. The idea is that cosmic rays from the nearest supernova could damage the ozone layer, resulting in increased ultraviolet radiation on the Earth's surface and harming life, especially shallow oceanic organisms. Although these theories are still being studied and debated, they highlight the potential impact of distant cosmic events on our home planet. It's a reminder that we're part of a dynamic and interconnected universe. As we look out into space, we're looking not only to the past but also the future. Stars will continue to be born, live, and die, and some of them will end their lives as supernovae. But what does the future hold for supernovae in our Milky Way galaxy? Astronomers estimate that a supernova explosion in the Milky Way occurs on average about once every 50 years. However, most of these supernovae are not visible from Earth because dust and gas block the direct view. The last supernova visible to the naked eye in our galaxy was over 400 years ago, observed by the famous astronomer Johannes Kepler. But rest assured, astronomers are keeping a close eye on potential supernova candidates. These include such stars as Betelgeuse in the constellation Orion and Eta Keel in the constellation Keel. Both massive stars have unusual behavior, leading astronomers to speculate that they could become supernovae in the relatively near future on an astronomical timescale. A recent study has shed new light on the mysterious behavior of that celestial giant Betelgeuse. This star, known for its semi-regular variations, has been the subject of intense scientific scrutiny. In the context of a star such as Betelgeuse, these changes are visible in brightness or intensity of light. The star does not follow a strict cycle of increasing and decreasing brightness, but rather oscillates in a predictable but not entirely regular manner. Researchers have identified 4 different periods in the variations of Betelgeuse: 2, 200, 420, 230, and 185 days. They suggest these periods correspond to the pulsation patterns of the star, in particular the radial principal mode and the first, second, and third overtones. This pulsation analysis, which takes into account the complex interaction between pulsation and convection, suggests that Betelgeuse is in the late stage of core carbon combustion. The study also looks at the previously mentioned event known as the Great Dimming, which caused Betelgeuse's brightness to decrease significantly from December 2019 to February 2020. Researchers speculate that during this period, the effective temperature of Betelgeuse dropped by about 100 K, which may have resulted in significant mass ejection of the star. This event triggered a flurry of observations and analysis aimed at deciphering the secrets of this distant star. The researchers' findings lead to an exciting conclusion. Betelgeuse could be the next star in the galaxy to go supernova. Given the current stage of late-burning carbon in the core, its high luminosity, and complex variations, Betelgeuse is a prime candidate for participation in this exciting cosmic event. The study also notes that the star's high rotation rate as a red supergiant has sparked discussions about its evolution, including the possibility of past mergers with another star as a source of angular momentum. However, it is important to note that predicting exactly when a star will go supernova is extremely difficult because it depends on many factors that are not fully understood. Even if a star has indications that it might go supernova, it could be thousands or even millions of years before it actually goes supernova. But rest assured, when it does, it will be a grand spectacle. The study of supernovae is crucial to our understanding of the universe. These stellar cataclysms are not only endpoints, but also beginnings. saturating the cosmos with the elements necessary for new stars, planets, and possibly life. As we travel through the cosmos, we're constantly reminded of the grandeur and mystery of the universe. Supernovae are a testament to the life cycle of stars, the creation of elements, and the interconnectedness of the cosmos. We have studied their types, the dangers they pose, their impact on Earth's history, and what the future may hold. These celestial events, as destructive as they are also creators. They seed the universe with the elements necessary for new stars, planets, and possibly life. Studying supernovae is not only about understanding these spectacular events, but also about understanding our place in the universe. They remind us we are made of star stuff, that we are part of this vast, dynamic, and constantly evolving cosmos. In 2021, the James Webb Space Telescope, or JWST, was launched from Kourou, France, to study at Lagrangian point L2 the cosmic bodies and distant galaxies around us, which can help us learn more about the birth of the universe. Equipped with large mirrors and revolutionary instruments, James Webb was able to make several important discoveries for the scientific world in just 1 year of the mission, including such complex cosmic processes as star formation and their death. Today, you'll learn about JWST's most remarkable discoveries to date, from the first detailed image of a cluster of galaxies to a new exoplanet. One of Webb's first images was of the galaxy cluster SMACS 0723, 4 billion light-years from Earth. It was not a discovery. The cluster was first explored by Hubble. However, thanks to its cameras, Webb was able to provide a very detailed image, revealing to scientists hundreds of previously unseen small galaxies. Interestingly, Webb made this image in just 12 hours, when it would have taken Hubble several weeks. Webb's photos will allow scientists to study young galaxies before they merge into larger spiral galaxies. For example, a study led by Rohan Naidu of Harvard University indicates that some galaxies there may have formed in as little as 300 million years after the Big Bang. In addition, scientists noticed elongated galaxies that also appeared simultaneously in different places. According to the research of astronomer Massimo Pascal, the cause of stretching may be the gravity of the galaxy cluster, which distorted the light, causing galaxies to appear in different places. The scientist also noted the elongation of SMACS 0723. It could be caused by its collision with assumingly another galaxy cluster. The next important image of Webb was a rare ring galaxy, the Cartwheel, 500 million light-years away. It was discovered back in 1941, but a detailed image was only obtained now. Its strange appearance, reminding us of a wooden carriage wheel with a circle in the center and diverging spokes, probably formed as a consequence of a high-speed collision between two galaxies over 400 million years ago. Therefore, it's likely that the Cartwheel galaxy looked just like our Milky Way before the collision. Moreover, Webb discovered that the core of the wheel contains a large amount of hot dust and that the brightest regions emanating from the center contain many young stars. That is, as the galaxy expands, it pushes dust and gas outward, forming stars. The Cartwheel galaxy is still transforming after the collision, so further observations by Webb could reveal more of the mysteries of this galaxy and also look at the star-forming process. In July of 2022, Webb captured the last moments of a dying star that had been emitting gas and dust for several millennia, forming the South Ring Nebula. This nebula, only 2,000 light-years away, was also explored by Hubble, but it only captured one star there, very bright in the infrared. As the emission continued, the star, which was 3 times the size of the Sun, shrank significantly, turning into a white dwarf. Because of this, the star could not shine brightly. Scientists then concluded that all the material ejected by the star must have formed a dust disk, and that would have glowed when heated. Such a dust disk could only be created by another star. Moreover, Webb noticed another oddity. The nebula has lines along its edges. It's unlikely that the dwarf itself could have created such patterns. Thus, Macquarie University astrophysics professor Ursula DeMarco believes that the white dwarf may have several companion stars that scattered all the material and created a disk around the central star. Finally, Webb confirmed that there is a second young star near the dwarf, although no other stars are visible. Scientists speculate that they are either too dim or have already been absorbed by the central star. Therefore, Webb's study will help scientists not only learn more about this association of stars, but also to study the chemical composition of the ejected material. In addition to the death of the star, Webb was able to capture its birth. Webb succeeded in capturing the bright clouds emitted by the newly formed star, L1527, at a distance of about 460 light-years. The star emits layers of dust and gas in different directions, so the appearance of this nebula resembles an hourglass. The color of the clouds is determined by the thickness of the dust, an orange color where the dust is denser and vice versa. The thinner the layer, the bluer the color would be. Scientists estimate that this star is only about 100,000 years old, when a star is formed about 10 million years or more. Also, NASA researchers believe that L1527 is already approaching the generation of its energy through nuclear fission, so it will soon be able to ignite on a cosmic scale. Moreover, the barely visible line that crosses the clouds is a protoplanetary disk, and it is the size of our solar system. Therefore, it is likely that planets could form around L1527, just as in our system. This, in turn, will not only allow us to observe what the solar system looked like when it formed, but also to consider these exoplanets as possibly inhabited. Another distant Kiel Nebula was the target of James Webb's research. The Kiel Nebula contains a region of star formation NGC 3324, the edge of which Webb captured in detail. The rock-like part of the nebula is actually hot, ionized gas and dust. Amid this nebula, Webb was able to capture with its cameras hundreds of previously hidden newborn stars. Moreover, the telescope also detected thin jets of hydrogen erupting from the top of the nebula. Such columns could probably indicate an active period of star formation. Such an event is very rare, and it lasts only up to 10,000 years. This discovery is a new step in the study of star formation and its effect on nearby planets and the entire nebula. In addition to the Kiel Nebula, Webb studied another nebula that could also bring scientists closer to a better understanding of star formation. The Pillars of Creation Nebula is about 6,500 light-years away in the Eagle constellation. In its huge columns of dust and gas, 4 to 5 light-years long, Webb discerned many young stars that are just forming. Take a look at the nebula's second pillar. The top of it is reddish and looks like lava. This means that there are stars in this area that are emitting jets during formation, which means they are estimated to be 100,000 years old. By the way, scientists also noticed that there should be more stars in this image. The fact is that stars have recently finished their development. They had got rid of the dust surrounding them, so it's difficult to see them in the mid-infrared. But nevertheless, the information from James Webb will be enough to investigate how stars form and emerge from these dust clouds. Webb's next discovery is of even greater interest to scientists. This time it is not a nebula, but the brown dwarf Glass JWST BD1 at a distance of about 2,000 light-years from Earth. Brown dwarfs are quite rare and dim and also have some of the characteristics of a planet. That is, they're not massive enough to synthesize hydrogen and emit starlight, but they also have an atmosphere like a planet, with the probable presence of water molecules in it. So studying why a star has so little mass will help scientists learn more about the boundary between planets and stars, and how they form. Now back to our dwarf. Very little is known about glass, JWST BD1 at the moment. It is about 30 times larger than Jupiter and has a temperature of about 720 degrees Fahrenheit. Brown dwarf researchers led by Mario Nannino said that further observations are needed to learn the star's chemical composition and properties. But in addition to glass, JWST BD1, Webb was also able to study the previously discovered brown dwarf, VHS 1256-1257b, specifically its dust clouds. VHS 1256-1257b is relatively close, 72 light-years away, so Webb was able to examine its atmosphere in detail. It found many important chemical elements there, including water and carbon dioxide, as well as a cloud of silicate particles. Thus, Webb was able to bring scientists a little closer to understanding the structure of dwarfs and exoplanets. The first exoplanet that Webb captured was the gas giant HIP 65426b. This young exoplanet, 385 light-years away, was discovered back in 2017 by a ground-based telescope. However, the study of the planet was complicated because it was quite difficult to get a detailed image with short infrared light waves, especially because of the large number of bright stars. For example, the star HIP 65426, around which the exoplanet orbits, is 10,000 times brighter than it. Nevertheless, Webb's cameras took the first direct image of the exoplanet during its mission. HIP 65426b is 100 times farther away from its parent star, so the telescope was able to spot the planet. Although Webb did not get a closer look at HIP 65426b because of the enormous distance, the images will help scientists learn more about the planet and the system as a whole, as well as opening up the possibility of taking pictures of other distant exoplanets. Another of Webb's first scientific mission targets was the WASP-39b exoplanet. It was previously observed by the Hubble and Spitzer telescopes, but Webb was able to provide an almost complete characterization of its atmosphere. WASP-39b is a gas giant slightly smaller than Jupiter with very low density, so life is unlikely to be possible there. It is about 700 light-years away from us and orbits a G-class star, WASP-39, similar to our Sun, though it's slightly smaller and cooler than our star, probably due to its older age. However, WASP-39b is the closest planet to the central star. It orbits at a distance of 4 million miles or 7 million kilometers, which is 8 times closer than Mercury to the Sun. That's why temperatures there are very high on average, 1600 Fahrenheit, and with its mission, Webb confirmed the presence of water vapor, sodium, and potassium in the atmosphere, which had been detected by previous studies. This year, Webb recorded sulfur dioxide, oxygen, methane, and for the first time on exoplanets, carbon dioxide, which amazed scientists. Sulfur dioxide results from a chemical reaction when it interacts with starlight. And by the way, on Earth, the ozone layer is formed as a result of the same interactions. In addition to the presence of oxygen, according to Kazumas Ono, a scientist at Santa Cruz University, it may indicate that the planet is migrating toward its current orbit. Such reactions have not yet been observed on other exoplanets, so WASP-39b offers scientists an opportunity to study the formation of atmospheres on exoplanets and the history of the formation of the planets themselves. And finally, in January 2023, it was revealed that Webb had been able to join the ranks of discovered exoplanets with its find. At a distance of about 40 light-years from Earth, Webb, observing a red dwarf, noticed how the light from the star covered the object orbiting it. In just 2 rotations or 4 days of the object around the star, Webb accurately determined it was a planet. Thus, exoplanet LHS 475b became the first planet discovered by Webb. Making a direct picture of the planet is not something Webb has had success with yet. However, researchers have already been able to give the first characteristics of LHS 475b. At this time, we know that this exoplanet is almost entirely the size of Earth. It has a rocky composition and has a fairly high temperature of about 100 degrees Celsius more than the Earth. It's not yet been possible to determine whether it has an atmosphere. However, if an atmosphere is detected, a group of scientists led by Jacob Lustig Jaeger believes it could be similar to Venus. Still more research is needed to establish whether there is an atmosphere there and perhaps even whether life could exist there. The James Webb Telescope has reached its research point in a year. Together with the scientists, they've about 9 more years of work ahead. Webb's main missions are the study of early galaxies, star formation, and the in-depth study of exoplanets and planets in our solar system. Shortly, Webb will probably study the TRAPPIST-1 system, some planets of which may be inhabited. Moreover, Webb will focus on studying the atmospheres of Mars, Pluto, Jupiter, and Kuiper Belt objects, which could provide more information about the origin of the solar system. Another mission for Webb is to investigate the sources of water in space objects. To do this, Webb will study Jupiter's icy satellite Ganymede, where there could be an internal ocean. This could also help further studies of icy ocean satellites like Enceladus, Europa, and possibly Mimas. Therefore, we expect that Webb will be able to make many discoveries over the years that will change our understanding of the universe. Beyond the orbit of Mars, among millions of asteroids, the inconspicuous dwarf planet Ceres floats as if to upset the entire cosmic order. Despite its seemingly boring appearance, little Ceres challenged all of cosmology, standing on a par with other planets as the very first dwarf planet known to mankind. But that's not the only thing that has baffled scientists. In a sea of dim meteors, gray Ceres shines like a small star through mysterious bright footprints that may hide cold ocean depths where the heart of life is likely to beat. Today, we're traveling with you into the icy depths of the asteroid belt to meet the small planet Ceres, its ocean depths, and its mysterious radiance. So hop on, we'll be there soon. Ceres was first discovered in 1801 by astronomer Giuseppe Piazza. Initially, the scientists assumed that Ceres was a comet, but because of its slow and even motion, like a planet, he revised his calculations and continued observations. Even before the astronomers' research, well-known theorists such as Johannes Lambert had suggested there should be another planet in the gap, or asteroid belt, between Mars and Jupiter given its width. Piazza stopped working on his most significant discovery due to health problems, but his attempts to explore the distant and dark planet and calculate its orbit did not gather dust. Mathematician Friedrich Gauss, using the very limited data that Piazza managed to collect, was able to calculate the approximate orbit of Ceres. In particular, other astronomers such as William Herschel were even able to calculate the diameter, but it was far from reality. The researchers found that the size of the planet was only 160 miles, but in fact, according to modern observations, Ceres' diameter is 584 miles. Giuseppe Piazza considered the object he discovered to be a planet, and yet for 3 centuries Ceres was considered by the wider scientific community as an asteroid. Only in 2006 did the International Astronomical Union finally recognize Ceres as a dwarf planet along with Pluto. The discovery of Ceres could not but leave a mark on modern astronomy. Thanks to the small planet, scientists have deepened their knowledge of how the solar system was born and planets formed. For the first time, we were able to see the embryo of a planet, or planetesimal, so close. Ceres has expanded everything we know about cosmic bodies by its existence, actually forming a new type of planet as a dwarf planet. Due to the difficulties of studying a dim and seemingly dead planet, scientists have long considered it just a large body in the asteroid belt. Its mass is about 25% of all objects in the belt, but still, even dwarf Pluto is 14 times more massive than it. In particular, it seems that due to the gravitational effect of Jupiter, a small planet could not form completely. It is at the embryonic stage, without any opportunity to gain mass from the building asteroids that surround it. It takes 4.6 Earth years to complete a full orbit around the Sun, but its rotation on its axis is only 9 hours, making its day one of the shortest in the solar system. Interestingly, the axis tilt is not visible to the planet at all. It's only 4 degrees, so there's no possibility of feeling seasonal changes on Ceres. The night on the dwarf planet is also absolutely dark because it has no satellites, unlike most other planets, and no rings. Ceres is too small to hold them in its orbit. The planet's 3 times more distant from the Sun than Earth, so the annual average temperature there drops to negative 100 degrees Fahrenheit. Any heat that gets to the surface of Ceres is unlikely to stay there for long. It probably lacks an atmosphere and even a magnetosphere that would protect it from the radiation effects of solar wind. It doesn't seem that such a planet would be able to harbor any life. But pay close attention to the surface of Ceres. Despite its age of 4.5 billion years old, its surface has only a small bunch of craters and no deep impact basin. One could assume the planet could have survived a collision with another massive object that would have broken off a giant chunk of it. But the explanation for this strange phenomenon is different, but no less surprising. In 2015, the Dawn spacecraft went on an expedition to Ceres. The data collected by Dawn showed a rather unexpected result. Having made a complete map of the dwarf planet's surface, scientists concluded that its surface consists of a mixture of ice and minerals such as clay and carbonates. Therefore, although it is similar to the Earth planet, its density is several times lower. Having studied the smooth surface of the craters, the very unusual bright spots on their bottom, and the furrow patterns across the surface, scientists came to the final conclusion that Ceres is geologically active. What makes its icy surface young again and again are cryovolcanoes. Ceres may consist of 25% water. This water pours out onto the planet's surface, filling deep craters with cryolava. Astronomers have noted that across the planet's surface, you can see rocks, canyons with faults, which may also indicate geological activity, and several dozen cryovolcanoes, with the highest of them being the inactive Ahuna, which is 4 miles high. Ahuna, surprisingly, is a fairly young volcano, having formed about 1 billion years ago, which means that until recently, Ceres had enough heat to form such a geological object. A study by scientists led by paleontologist Maria Cristina de Sanctis found that some volcanoes may still be active, given the bright trail we'll return to later. The activity of these volcanoes is important, not only for the planet's surface, but also for its atmosphere. Due to eruptions or degassing, the atmosphere can be saturated and retain more and more heat. However, Ceres is not a simple case. Its gravity is not strong enough to maintain a permanently dense atmosphere. Instead, Ceres' atmosphere is variable, meaning it sometimes appears and then disappears. This is all due to solar activity. When the sun heats the ice very strongly, it sublimates, forming a temporary exosphere, and that disappears in a few weeks. At present, scientists working at the European Southern Observatory's Very Large Telescope see no hints of atmospheric recovery shortly. The 57-mile Ocator crater has drawn another serious attention. It was formed 20 million years ago after a likely collision with a very massive object. After the impact, Ceres' crust cracked, releasing much water, which formed long furrows and patterns. The water also washed clay-forming minerals rich in magnesium and ammonium, known as phyllosilicates, to the surface, along with an unusual marine mineral called hydrogolite, and that was found only on Earth. That brings us to another interesting discovery. Ceres may be an oceanic world. Under the icy surface of a dwarf planet, there could be deep subsurface liquid ocean, but that was in the distant past. Now, most likely, the inner ocean is frozen, but not completely. Liquid, salty water deposits still exist beneath the surface. Their depth can reach an average of 25 miles, and it's likely that water ice with various gases, such as methane, can make Ceres' crust insulating, thus heating the water internally. Scientist Maria Cristina de Sanctis says that the ocean on Ceres had no reason to exist and should have been frozen by now. But Dawn's research has shown part of it could have survived under the surface. The temperature of these remnants of water can be as low as -22 Fahrenheit, and that's due to the large amount of salt and a mixture of other minerals to stay in a liquid state. According to Dr. Moore, Ceres cannot receive heat from, for example, tidal energy, from orbiting a more massive object like Saturn's moon, Enceladus, and thus keep the entire ocean inside liquid all the time. The impact that formed Ocator became the main driver of cryovolcanism on Ceres, bringing cold water from the ocean to the surface, leaving behind the same strange bright traces that allowed us to confirm the presence of water on the planet. So what are these mysterious marks? At the bottom of Ocator and other craters like Cerealia Facula, scientists have noticed large, shiny traces that reflect almost 50 to 60% of all the light that hits them. And the origin of these traces has been puzzling to researchers. At first, the bright spots were thought to be just ice plumes or traces of ammonia or methane, but now scientists are developing another theory. Likely the answer to the mystery of what all these bright spots hide is salt. After cryolava erupts from saltwater reservoirs, the substance gradually evaporates, leaving behind a salt crust containing magnesium sulfate, Epsom salt, and sodium carbonate. In total, the Dawn mission recorded more than 300 such bright areas. Interestingly, however, they all differ. The brightest spots are located at the bottom of craters and consist of salt-rich material mixed with water. Another group of bright salt deposits can be found in the form of streaks and patterns, diverged from the craters as a result of collisions with meteoric bodies. According to researcher Nathan Stein, over hundreds of millions of years, bright material has mixed with dark material to form the bulk of Ceres' surface. This indicates that billions of years ago, there were many more collisions with the dwarf planet and more than 1,000 bright spots. But why are some spots brighter than others? The process of creating such areas can also be quite specific and unique. For example, there's probably a reservoir of water under Ocator, so cryovolcanic activity increases its brightness more intensely. The Cerealia Facula crater with a slightly less bright spot could have formed in a more complex way. Cryolava could have moved slowly upward, creating a dome inside which material was boiling all the time until it settled as a mixture of ice and salt pieces on the surface. This whole process of forming bright patches of salt has not yet stopped. Paleontologist Maria de Sanctis has found evidence of traces of sodium chloride in Ocator, and after coming to the surface, the water component of this salt should have boiled off within 100 years, but the salt still remains moist. The bright spots again prove the fact of geological activity on Ceres, which is important for the most important process on every planet, the formation of life. As cold and inhospitable as Ceres may be, it meets many of the necessary criteria for the emergence of simple microorganisms and may already have life among its icy layers. Liquid water is the main environment in which life can arise. But of course, to form even an organism's embryo, various chemical elements are needed, the most important of which is carbon. Carbon is used to form the skeleton of living organisms and other crucial chemical compounds. Therefore, knowledge about the composition of the dwarf planet's surface will help answer the question of the possibility of life there. Thus, according to the data collected by Dawn, Ceres' surface contains a lot of silicate and iron rocks, but carbon also makes up a very significant proportion. About 20% of the surface mass consists of organic, 5 times more than in carbonaceous chondrite meteorites on Earth. Moreover, the analyzed carbon is mostly mixed with water and clay. Such mixtures, when combined with oxygen and hydrogen, create a variety of organic compounds including sugars, alcohols, and fats. However, this is not the only chemical element important for the development of life that's available on the planet. Water itself already contains a whole range of compounds. Materials on the planet have undergone significant change over billions of years. For example, rocks, such as serpentine and carbonate minerals in the interior of Ceres, melted due to radioactive decay inside the planet, forming rocks similar to shale. The newly formed material probably formed pockets of salty liquid, filling the water with various substances, such as sodium, sulfur, methane, etc. Such a soup of building blocks could be a niche for life, according to geophysicist Mohit Daswani. But more than that, millions of years ago, when there were more collisions and thus the planet received more heat, simple microbial life could hypothetically exist. Therefore, primitive life could probably develop in water tanks right now. However, the problem is still the absence of an atmosphere for a long period of time that would prevent the surface from strong radiation. In particular, the exact amount of liquid water is not known to say for sure that life has a place to form, and in addition, the Dawn mission did not confirm the presence of large amounts of nutrients such as nitrogen or phosphorus, which are necessary for any life activity. Only future missions and soil samples can determine whether Ceres is habitable. In more than 10 years, NASA astronomers plan to send a new expedition to Ceres to collect a sample from the planet's surface. Researcher Dr. Julie Castillo-Roguez says the proximity and low gravity of the planet will allow them to return samples at a relatively low cost. The doctor is confident that there will be organic matter in Ceres salts, which gives us more hope that we can finally find out if we're alone, at least in the solar system. Ceres is an ideal natural laboratory that offers scientists many opportunities to explore the history of our solar system and the origin of life in difficult conditions. Such an intriguing object as the dwarf planet Ceres is of almost unprecedented importance in the study of planetary evolution, and the study of its geological features will allow us to model the entire cycle of planet formation. Future research may be crucial and a breakthrough for all of cosmology. Ceres could hypothetically become one of the first planets on which humanity will find new life. Perhaps this small and inconspicuous dwarf planet will also draw the attention of scientists to dozens of other similar icy oceanic worlds that also have many secrets.